pleasant day to you, our dear students. We welcome you for this academic year 2021-2022. But before we begin with our discussion, I would just like to introduce to you the teachers in General Physics 1. First, we have Miss Mika Margaret C. Andres, the teacher of section Saint Agatha, Saint Juliana, Saint Christina, Saint Dymphna, Saint Aquilina, and Saint Clare. Second, we have Miss Jilmay M. Lubin, the teacher of section Saint Gertrude and Saint Rose. And lastly, I am Miss Angelou D. Caole, and I am handling sections Saint Justina, Saint Cecilia, Saint Victoria, Saint Martina, Saint Brigid, and Saint Philomena. And so, we welcome you in the world of physics. Just a short description about General Physics 1. General Physics 1 is all about the mechanism of particles, rigid bodies, fluids, waves, heat, and thermodynamics using the methods and concepts of algebra, geometry, trigonometry, graphical analysis, and basic calculus. Let's have the learning content for today's discussion. First, we have the significant figure. Second, we have the scientific notation. Third is the quantities, measurements, and units. Fourth is the conversion of units. Fifth is the scalar and vector quantity. And sixth is the component vector. So let's proceed to our first topic. We have the significant figure. So what is significant figure? Okay, significant figure are digits in the number that are reliable and absolutely necessary to indicate the quality of something. Okay, so we have 5 rules to consider under significant figure. Okay, rule number 1 under significant figure, we have non-zero digits are always significant. Now, what do we mean by non-zero digits? These are numbers from 1 to 9. In example number 1, we have 38.57. So we have 4 non-zero digits, therefore we have 4 significant figures. And in example number 2, we have 288 grams. Okay, we have 3 non-zero digits, that is why we have 3 significant figures. For the rule number 2, zeros are sometimes significant and sometimes are not. Okay, we have sub-rule letter A. For rule number 2, zeros at the beginning of a number that are used just to position the decimal point are never significant. So we have first example, it's 0.052. These 2 zeros here are not significant. Therefore, we only have 2 significant figure, for example, number 1. While in example number 2, 0.00364 meters, okay, these 3 zeros here are not significant. Therefore, we have 3 significant figures for example number 2. Another sub-rule for rule number 2, zeros between non-zero digits are always significant. Okay, zeros between non-zero digits are always significant. For example, we have the 2007. Okay, zeros are in between 2 and 7, therefore we have 4 significant figures. And we have 6.08, that is the 0 is in between 6 and 8, therefore we have 3 significant figures. For letter C, trailing zeros in a whole number with the decimal shown are significant. Okay, I repeat, trailing zeros in a whole number with the decimal shown are significant. For example, we have 38.0 centimeters. Okay, so we have 3, 8, and 0 as significant figures. And for example number 2, we have 440.0 meters. We have 4, 4, 0, and 0 as significant figures. So in example number 1, we have 3 significant figures. And in example number 2, we have 4 significant figures. Last but not the least, for rule number 2, zeros at the end of a number that does not contain a decimal point may or may not, okay, may or may not be significant. For example, we have 24,300. So the number of significant figures here may be 3, 4, and 5. Okay, so it's 3, 4, and 5 because we have 5 digits here. So 2 and 4 and 3 might be significant. 2, 4, 3, 0 might be significant. And of course, 2, 4, 3, 0, and 0 might be significant. For rule number 3, exact numbers can be considered as having an unlimited number of significant figures. Okay, for example, we have 1 yard. So if the given is 1 yard, of course we have one significant figure. But then 1 yard is also equivalent to 3 feet and 1 inch, right? And 3 feet and 1 inch is also equal to 91.54 centimeters. That is why exact numbers are not applicable to significant figures. Rule number 4, in addition and subtraction, the last digit retained in the sum or difference is determined by the position of the first doubtful digit. So what is a doubtful digit? Doubtful digit refers to the last digit or the smallest number of digits in the decimal place. For example, we have 37.24 ml plus 10.3 ml is equal to 47.54 ml. I repeat, doubtful digit refers to the last digit or the smallest number of digits in the decimal place. So we have 10.3, right? So our answer will be reported as 47.5 ml. Okay, for subtraction, we have 27.87 minus 21.2342 grams is equal to 6.6358 grams. Okay, our doubtful digit is the 27.87 or the 0.87. That is why our answer will be reported as 6.64. Rule number 5, in multiplication and division, an answer contains no more significant figures than the least number of significant figures used in the operation. For example, what is the area of a rectangle 1.23 centimeter wide and 12.34 centimeters long? So look at the given and determine what is the smallest number of significant figures. Okay, so we have 1.23 and 12.34. So automatic that our answer will be expressed in 3 significant figures only because of the 1.23 centimeter. Okay, so the formula in getting the area, we have the length times width. So 12.34 centimeters times 1.23 centimeter is equal to 15.2 centimeters squared. Next, we have the scientific notation. Okay, scientific notation is a way of expressing numbers that are too large or too small to be conveniently written in decimal form. The primary reason for converting numbers into scientific notation is to make calculations with unusually large or small numbers less heavy or too long. We also have rules in expressing numbers into scientific notation. First is moving the decimal point. Okay, move the decimal point until there is a single digit from 1 to 9 at the left position of the decimal point. For example, we have 12,234,000. So we have to express that in the scientific notation. Therefore, let's move the decimal point from here, okay, going to the single digit at the left. So we have like this. Okay. After moving the decimal point, we have to count how many places the decimal point moved. Okay, the number it moved will be the exponent of the 10 in the notation. So let's count from this point originally going to left until we reach the single digit. So we have 1, 2, 3, 4, 5, 6, and 7. Okay, so we have 7 moves. And now we are ready to express the number in scientific notation. So we have 1.2 times 10 raised to 7. Okay? It's 1.2 times 10 raised to 7. Remember that if you move the decimal point from right to left, the exponent is positive. But if you move the decimal point from left to right, the exponent will be negative. Okay, so let's try these examples. First, we have 10,042,017. Second, we have 212 10,000s. Third, we have 312,125. Fourth, we have 911 billions. And 5, we have 2,300. So let's start with number 1. I repeat, if it's from right to left, the decimal or the exponent is positive. But if it's from left to right, the exponent is negative. Okay, so for number 1, we will begin from the right going to left. So 1, 2, 3, 4, 5, 6, 7. Okay, so we have 1.0 times 10 raised to positive 7. Okay, for number 2, we have 1, 2. Okay, so it's 2.12 times 10 raised to negative 2. Okay, for number 3, we have 1, 2, 3, 4, 5. So the answer is 3.12 times 10 raised to 5. Okay, for number 4, from left going to right, we have 1, 2, 3, 4, 5, 6, 7. Okay, so that's 9.11 times 10 raised to negative 7. Okay, for number 5, we have 1, 2, 3. Okay, so that's 2.30 or 2.3 times 10 raised to 3. Okay, so those are the examples of scientific notation. Next, we have the quantities, measurements, and units. So what are quantities? Okay, quantities refer to the amount or number or any numerical value of a material or immaterial thing. So we have two types of quantity. First is the fundamental quantity and second is the derived quantity. Okay? For measurements, measurements is the estimation of ratios of quantities. And for units, these are used as a standard for measurement of the same kind of quantity. As I have mentioned, there are two types of quantity. First is the fundamental quantity, and second is the derived quantity. So fundamental quantity is an independent physical quantity that is not possible to express in other physical quantities. For example, we have length. Okay, the unit of length is meter. Its symbol is M. Okay, we have the mass, the unit is kilogram, its symbol is kg. For time, the unit is second, its symbol is S. Temperature, it's Kelvin, the symbol is K. For electric current, the unit is ampere, its symbol is A. Luminous intensity, the unit is candela, symbol is CD. And last, we have the amount of substance, its unit is mole, and the symbol is mole or MOL. So those are your fundamental quantities. Next, we have the derived quantities. Derived quantities are derived or calculated from two or more fundamental quantities. For example, we have the displacement, the area, the volume, the speed, the velocity, the acceleration, the force, the energy, the density, the momentum, the power, work, and the pressure. So those are your derived quantities derived from the fundamental quantities. Next, we have the conversion of units. As I've said, units are used as a standard for measurement of the same kind of quantity. For example, we have 36 meters and then we have to express that in millimeter. Okay, so always remember that 1 meter, okay, we have here 1 meter is equal to 1000 millimeters. Therefore, write the 36 meters times and then always express the conversion factor as 1 meter is equal to 1000 millimeters. Okay, so 36 times 1000 millimeters, that is 36,000 millimeters. Another examples. First, we have 2.25 kilogram to pounds. Okay, so 1 kilogram is equal to 2.205 pounds. Therefore, we have 25 kilogram times 2.205 pounds is equal to 55.13 pounds. For the second example, we have 3.78 miles. Convert it into kilometer. So 1 mile is equal to 1.609 kilometer. Therefore, 3.78 miles times 1.609 kilometer is equal to 6.08 kilometers. Okay. For the third example, we have 4.45 meters per hour. Convert it into inches per minute. So we have 45 meter per hour. Always remember that 1 meter is equal to 39.37 inches and 1 hour is equal to 60 minutes. Okay, so we have 45 times 39.37 inches divided by 60 minutes is equal to 29.53 inches per minute. Okay, so take note, you have to cancel all same units. So we have kilogram kilogram to come out with pounds. Okay, we have miles and miles to get the kilometer as a unit. And we have to cancel meter and meter, R and R, to have the inches and minute as our unit. Okay, let's have more examples under conversion of units. First, we have 24 kilometer to meters. So, we're going to write our solution here. So, we have 1 kilometer is equal to 1,000 meters. Okay, so we have 24 kilometer times, oh, this is kilometer. 1 kilometer is equal to 1,000 meters. So cancel kilometer to kilometer. Therefore, we have 24,000 meters. Okay, so 24 kilometer is equal to 24,000 meters. That is for example number 1. For number 2, we have 123 meters to kilometers. Okay, so we have 123 meters times, okay, just write 1 kilometer at the top, and then 1,000 meters at the bottom. Since we have 1 kilometer is equal to 1,000 meters. So 123 meters divided by 1,000 meters, okay, we have 0.123 kilometer. Of course, cancel out meter to meter. So 123 meters is equal to 0.123 kilometer. Okay, for number 3, we have 49 inches, 2 centimeters. Okay, always remember that 1 inch is equal to 2.54 centimeters. Okay, so we have 49 inches times, just write 1 inch here. Okay, 1 inch is equal to 2.54 centimeters. So cancel inch to inches. That is 49 times 2.54 centimeters is equal to 124.46 centimeter. Okay, so 49 inches to centimeter is equal to 124.46 centimeters. For number 4, okay, 12 feet to meter. Okay, also remember that 1 foot is equal to 0.3048 meter. Okay, so 12 feet times, we have to write 1 foot here, 0.3048 meters is equal to 3.66 meters. Cancel feet and feet. Okay, so we have 3.66 meters. 12 feet is equal to 3.66 meters. Okay, for number 5, okay, we have 1.21 times 10 raised to 22 seconds. Convert it into hours and then express it into days. So we have, of course, remember that 1 day is equal to 24 hours. And 1 hour is equal to 3,600 seconds. Okay, that's 60 times 60. Okay, so let's write our conversion here. It's 1.21 times 10 raised to 22 seconds times, okay, we have to write here 1 hour, okay, that is equal to 3,600 seconds times, okay, 1 day is equal to 24 hours. Okay, so cancel seconds to seconds, hour to hours to get the unit day. Okay, so 1.21 times 10 raised to 22 divided by 3,600 divided by 24 hours, I believe that is 1.40 times 10 raised to 17 day. Okay, so that's it. That's how you convert your unit into its desired unit. Okay, so let's proceed with the scalars and vectors. So scalar is a quantity that has a magnitude but no particular direction, while vector is a quantity that has a magnitude and acts in a particular direction. I repeat, scalar is just a magnitude, while vector has magnitude and of direction. Okay, we have here quantities, and we have to identify if the quantity given is a scalar or a vector quantity. So first we have 39 degrees Celsius. Obviously, it's just a magnitude. Therefore, it's a scalar quantity. For number 2, it's 1,000 kilometers. It has a magnitude and direction. Therefore, it's a vector quantity. For number 3, we have 500 Newton, 30 degrees northeast. That's a vector quantity. For number 4, it's 50 kilometer per hour. Obviously, it has no direction, so that's a scalar. Number 5, 1,500 joule. Okay, that's scalar. For number 6, 500 gigabyte. That's a scalar quantity. For number 7, it's 100 hertz. Of course, it's a scalar. For number 8, it's 3 times 10 raised to 8 meters per second. It's a scalar. For number 9, 1 year. Okay, it's also a scalar quantity. And last but not the least, we have 250 kilogram meter per second to the left. So that's a vector quantity. I repeat, scalar quantity has magnitude but has no direction, while vector quantity has both magnitude and direction. Okay, so we are down to the calculation of the resultant vector or resultant displacement. It says here that if you have the same direction of displacement or vector, you are just going to add them. For example, a man walks 54.5 meters east, then another 30 meters east. Calculate his displacement relative to where he started. So we have dr as the resultant displacement is equal to d1 plus d2. Okay, your d1 is 54.5 meters plus your d2 is 30 meters. Okay, so 54 plus 30, that is, okay, 84.5 meters. And of course, you just need to copy the direction. It's east. So if we are going to illustrate that using the Cartesian plane, okay, so this is your east, south, west, and north. Let's have the first displacement, assuming that this is already 54.5. Okay, so this is your D1, and then let's also have the D2. Okay, assuming that this is 30 meters. Okay, so we just need to add them to get the resultant displacement, which is equal to 84.5 meters, of course, due east. So that's how you get the displacement or the resultant displacement if you have the same direction. Example number 2. A man walks 54.5 meters east, then 30 meters to west. Calculate his displacement relative to where he started. In this example, we are dealing with two different directions. That is why we are going to subtract those two displacements. So we have the formula. dr is equal to d1 minus d2. Okay, d1 is 54.5 meters minus d2 is 30 meters. So 54.5 minus 30, that is equal to 24.5 meters. Now we have to follow the direction of the longer displacement, which is due east. Okay, and if we are going to illustrate this example, okay, we have to draw the Cartesian plane. This is your east, this is your north, west, and south. Okay, first is a man walks 54.5 meters east, assuming that this is already 54.5 meters, and then 30 meters west. So from this point going to 30 meters west, so we have to go back. So assuming that this is already 30, okay, this is already 30 meters, and therefore the resultant displacement is from the end point of the distance 1 up to the axis, point of axis. So we have dr, okay, and your dr is equal to 24.5 meters due east. So our final answer is 24.5 due east. Third example, a man walks 95 kilometers east, then 55 kilometers north. Calculate his resultant displacement and its direction. So, in order for us to imagine the problem, we are going to illustrate it first. Okay? So, for example, we have to draw the Cartesian plane, of course. North and east. Okay, this is your east, south, west, and north. So a man walks 55 kilometers east, 55 going to east, assuming that this is already 55, or 95 rather. This is 95 kilometer. Okay, and then 55 kilometers north. So for example, this is already 55. 55 kilometers north. Now calculate his resultant displacement and its direction. Now we have to compute first in order for us to get the resultant displacement and of course its direction. We have the formula dr is equal to the square root of d1 squared plus d2 squared. Okay, for your d1 we have 95 kilometer squared plus 55 kilometer squared. Okay, so my final answer here is 109.77 kilometers. Okay, in order for us to get its direction, we have to use this formula, which is theta is equal to tan negative 1 y over x. Okay, since 95 kilometers lies in east, which is in the x-axis, and 55 kilometer is in the north, which is the y-axis, therefore we have y as the 55 kilometers and 95 kilometers, or x as the 95 kilometers. So we have here tan negative 1, substitute the given, it's 55 km or kilometers divided by 95 kilometers. Okay, my answer here is 30 degrees, 30.0 degrees. Of course, cancel kilometer to kilometer. Okay, so our angle is 30 degrees, which we are now ready to illustrate our resultant displacement. Okay, so that is 30 degrees northeast. Okay, so from east going to north. I repeat, if I say northeast, it's from east going to north. So it's 30 degrees, for example. Okay, so we have 109 point, relatively longer, 109. Okay, so assuming that this is our 30 degrees, of course you can illustrate this better if you have your protractor and your ruler with you. Okay, so our resultant displacement is 109.77 kilometers. Okay, so that's how you solve problems with different direction, and of course in finding for its resultant displacement and its direction.
So for our last example, we have vector A is equal to 21 meters, 45 degrees north of east. Vector B, we have 12 meters, 75 degrees north of west. First thing to do is to illustrate the given. Let's have the Cartesian plane. Indicate its directions. We have east, south, west, and north. For vector A, that is 21 meters, 45 degrees north of east, assuming that this is already 45 degrees, and the magnitude is 21 meters. For letter B, we have 12 meters, 75 degrees north of west. So assuming that this is already 75 degrees, and this is your vector B. Now let's find for the x and y component of each vector. We have ax is equal to a cosine theta. Okay, indicate or write the value of a, that is 21 meters cosine 45. This is equal to 14.85 meters. For the ay, we have a sine theta. It's 21 meters sine 45. This is also 14.85 meters. This should be in degrees. Okay. For the b vector, we have bx is equal to b cosine theta. Okay. Indicate the value of b, that is 12 meters, cosine, and the angle, okay, from the b vector up to the angle going to the x-axis. So we have from this going to the 0 of the x-axis. Okay, so we have 45 plus 45, 90 plus 15. That is equal to 105. So the angle that we are going to use for the bx and by is 105. Okay, so 12 meters cosine 105 is equal to negative 3.11 meters. I repeat, in getting the angle, that should be in relative x-axis or in relative to the x-axis. B sine theta is equal to 12 meters sine 105. Okay, this is 11.59. Now that we have the x and y component of each vector, we are now ready to get, okay, its summation. So for the summation, we have Rx is equal to Ax plus Bx. Substitute 14.85 meters plus negative 3.11 meters. This is equal to 11.74 meters. And for the Ry, it's Ay plus By. So we have Ay is equal to 14.85 meters plus 11.59 meters. And that is equal to 26.44. meters. Now, to get the resultant vector, we have to use the Pythagorean theorem, which is R is equal to the square root, okay, of Rx squared plus Ry squared. So Rx, that is 11.74 from this value, plus your Ry, that is 26.44 meter squared. Okay, let's compute. Square root of 11.74 squared plus 26.44 squared. We got 28.93 meters. And for the angle, okay, let's write here, theta is equal to tan -1 Ry over Rx. Okay, so that is equal to tan -1. Your Ry is 26.44 meters divided by 11.74 meters. Okay, cancel meter to meter. So let's compute. Shift tan -1, 26.44 divided by 11.74. That is equal to 66.06 degrees. Okay, so for our resultant vector, which is equal to 28.93 meters, and for its direction, it's 66.06 degrees. Therefore, we are now ready to illustrate the resultant vector. So from east going to north, that is 66.06. Okay, let's erase this one. Okay, and try to illustrate it again. It's 45. Okay, this is 45 degrees. So from E going to north, or from east going to north, we have 66 degrees, assuming that that is already 66 degrees, okay? Let's have the resultant vector, which is relatively longer. So we have 28.93. Okay, so this will now be our resultant vector. Okay. Before we end, allow me to read this. It is important to measure certain things right, such like distance, time, and accuracy. By measuring these things, we can better understand the world around us. Life, as a matter of fact, cannot succeed if there is no such thing as measurement, because the Creator gave us the exact amounts of everything we are made of in order for us to live. That's all. Thank you and God bless.